is by Zoom, if I remember correctly.
Yes, hello.
Yes, it's Janne. Oh, hello.
Yeah, hey.
How are you?
I'm good. I'm good.
Very good.
How are you guys there?
Very good.
Paris?
Good that you're ready a bit ahead of time. Nice to see you again.
Yeah.
We saw you yesterday.
Likewise.
And unfortunately, we are not seeing you here this year. Do you want to introduce yourself and start the presentation?
Certainly.
Thank you.
Good morning, everybody. My name is Janne Mikola, and I work for Telia Company. So Telia is, for those who don't know, we are a service provider here in the Nordics and Baltics. Yeah, we're mostly operating in the 7 countries of Finland, Sweden, Norway, Denmark, Estonia, Lithuania, and Latvia. And yeah, I'm product manager for SD-WAN at Telia. And Telia SD-WAN is like actively being sold and deployed mostly in the Nordic countries, so Finland, Sweden, Norway, and Denmark. Baltics are coming later. But yeah, that's me. Next slide, please. So today, okay, so I can see that the fonts are not like maybe working perfectly, but let's hope that the presentation still makes sense. So that nothing gets kind of scrambled. But yeah, my topic for the presentation is artificial intelligence and machine learning in SD-WAN. And this is definitely coming from the service provider perspective. So you can put to the next slide, please. Yeah, for the most part, this looks fine. So, I mean, there are certain like prerequisites on implementing machine learning in the use cases of SD-WAN, and most of them have to do with the data, and pretty much all of them have to do with the data. I mean, there needs to be enough of some type of machine readable data that is like almost like bordering on big data. The data itself, it needs to be of high quality. Meaning that, I mean, whatever we are measuring, whatever data we are collecting, it should have as few like as possible of any types of gaps or errors or duplicate entries or any like false information. I mean, most likely any system will have some of this. I mean, any system will have outages. I mean, just the laws of physics simply dictate that sometimes, you know, in the digital transmission of data, some errors emerge into the network. So sometimes there will be errors, but the data still should be like the highest possible quality. And the storage and location of that data, it also should be like central. And this is because there are certain high requirements on both the disk I/O and the CPU consumption when actually running the machine learning jobs. And especially from my perspective, for the use cases that Telia is implementing at this point in time, we are really interested in any data that is like stored in a time series, basically. So, I mean, that's not the only use case you can implement machine learning for. The use case also could be like location or position. I mean, it could be prediction of where something is in the future and so on. But for us, I mean, we're looking at data that is in time series and usually stored in a time series database. For the use cases themselves, I mean, like I pointed out in the debate as well, I mean, the use case selection is extremely important. I mean, even if you have perfect data, even if it would be absolutely perfect, you could still kind of mess up the machine learning implementation by choosing use cases which are inherently random. And thus they wouldn't be predictable even, I mean, however intelligent and capable system with however processing power you throw at it. So I have some examples there, like, well, first of all, of course, an artificial, like totally random system, even if you throw machine learning at that, you will not get any sensible results out of it. But still, I mean, system can have a certain level of randomness, but still it could be predictable with machine learning. And as an example, I mean, these examples are not from the networking yet, but as an example, weather is such a system that can be predicted with machine learning. But then, I mean, sometimes the system can get so complex that probably no scientist on Earth kind of understands it well enough and to apply machine learning or any other type of AI on it, and stock market is such an example. I mean, we can jump to the next slide. I mean, now getting a little bit closer to networking and the service provider perspective, and SD-WAN especially. In many businesses, I mean, definitely businesses gather data. They have like centralized storage of data, for instance, in a department store or hypermarket. The kind of cashier machines, they definitely gather data, but and usually, I mean, there are high kind of reasons to have the data as high quality as possible, because of course no mistakes should be happening when like you know, doing the caching event of the customer. But still, I mean, the data is not necessarily yet usable for machine learning, and I will get back to that in a bit. But for SD-WAN, I mean, definitely we are gathering that type of data, and we are storing that centrally, and it is in time series form. You know, the networks today, especially the SD-WAN, I mean, one of the main selling points of SD-WAN is the kind of increased visibility into the network traffic. Compared to kind of a legacy VPN solution, SD-WAN already has an inbuilt capabilities gathering this telemetry information, which is way deeper than anything that a kind of traditional MPLS VPN is collecting from the network. So we go in SD-WAN, we go into the deep packet inspection, we are application aware, and we have all kinds of other characteristics that we are measuring and collecting the data from the devices, like you know, top talkers in the network and so on. Definitely these types of things are implementable in legacy networks as well, but they're not a built-in part of the, let's say, MPLS VPN deployment. You need separate and you know, additional components and equipment in order to implement that. We can go for the next slide. I mean, one thing that happens to be a little bit even like too good for SD-WAN is and networking as well overall, compared to, for instance, the I mean, the cashier machine type of a use case. Certainly, I mean, there will be timestamps in the cashier machine as well. I mean, it will be visible in the receipt that when was the sales done. But in networking, I mean, for multitude of reasons, we are anyway synchronizing all of our networking equipment with NTP, and we are having very highly accurate, like, you know, up to many decimals in the timestamps often, depending on what type of data we are looking at. And I mean, in the cashier machine use case, I mean, even if the timestamp is there, it might not be a meaningful part of the data. I mean, if you consider that there is a department store that sells, I mean, this is a made-up use case, but if they sell 700 LCD TVs throughout a year, I mean, how meaningful is the component of the data that at what time of the day did the sales occur? I mean, you might get two different timestamps that on a given day, you know, around 9 a.m. and 2 p.m. you made a sale of an LCD TV. But is that gonna be like impactful in some way that you can apply machine learning for that? But, you know, if you compare that time frame, you know, one given day from 9 a.m. to 2 p.m. To networking, and the fact that we are gathering that SD-WAN type of a highly deep and detailed data from the network telemetry data, I mean, it's multiple megabytes, even if not more, of the telemetry data that we gather from the networks during those, what is it, like 5 hours of the day. So there is huge difference, and applying machine learning for the bigger amount of data versus the 2 data points that you have for a given day, it's most likely going to provide better results. We can move to the next slide. I mean, one question that I often hear when I'm pushing for the implementation of machine learning here at Telia is that, I mean, why do we even need it? Why don't we just manually set the thresholds and you know, do monitoring as we do today? I mean, we call it proactive monitoring, and we have very capable tools for that, and we can set thresholds and we can set different, you know, functions there, that if that many alerts come in a certain given, you know, given time window, then let's react and so on. But the problem is that networks are not stable. I mean, they behave differently as a function of time, and any network engineer knows that. So basically, you can see a kind of a typical image of a network behavior. I do believe that is an actual screenshot of a elastic deployment that we have, an actual machine learning job. You can actually see in that picture as well the unsupervised learning in action. So you can see how it's like first building the shape of the predicted area before, and that's relatively wide before it is able to narrow down into a specific expectation, and then it's adjusting. As you can see, it's not a similar expectation or similar prediction from cycle to cycle. I mean, every cycle is actually different, and the machine learning entity within the elastic stack, it has its, let's call them, its own reasons to adjust the prediction. And interestingly, in that data as well, you can see one single gap in the data, and the machine learning job is like understanding the situation as well, that these things happen. It's not necessarily automatically like affecting the prediction that much. But the point is that networks are cyclical. So I mean, any kind of threshold setting in network monitoring is very, very difficult. And I mean, usually, whatever type of thresholds you set, I mean, you're mostly hitting the very extremes only. And also the problem is that when the networks grow, as we hope that every SD-WAN deployment that we deploy for our customers is growing over time, you would need to be readjusting those thresholds as well. And that's like a very big job, actually. I mean, if we are getting a new SD-WAN customer and we start discussing with the customer of the network and trying to figure out the specific and functional thresholds for certain variables in the network, which we could be monitoring on. I mean, we are not the experts of the network yet. This is a new customer for us, and we are in the discussion with the customer, and you can guess that the first ideas that we have of the thresholds are not going to be that good. I mean, they're going to be off by a little in the very beginning, and if we would continue that as an kind of iterative work, we would end up in a good thresholds for the monitoring over time. But the problem is that you would need to be adjusting these thresholds all the time because of the cyclical nature of the network and also the network growth. And because I just explained, the threshold setting actually is an iterative work that takes a little while to actually hit the correct level. I mean, that equation simply doesn't work. But in machine learning, we don't set any thresholds. I mean, that's completely left to the machine learning algorithm, the AI, basically. And thus, I mean, machine learning is definitely, from my perspective and from Telia perspective, making the impossible possible. We can go for the next slide. I mean, the use cases that we are now doing with machine learning here, we are at this point in time definitely relying on unsupervised anomaly detection or unsupervised learning only. So we have identified a bunch of different AI methods there, like they have been mentioned in the debate and in other presentations, like deep learning, reasoning, different pattern recognition, like image recognition, speech recognition types of things, classification that I actually do see as a very interesting AI capability, AI method for the network use cases. I mean, for the immediate future, and supervised learning as well, which is like relatively close to what we're doing with unsupervised learning, but it only opens up some possibilities of especially applying machine learning for such a complex use cases where the unsupervised learning is incapable of doing so by itself. So the idea with unsupervised learning is that it's like completely closed system from the service provider or the operator or the user perspective. So the machine learning algorithm in itself, it has the capability of looking at the data and learning over time. And how long that is, I mean, especially what I see in the cyclical nature of the networks, it usually takes a couple of cycles, like a couple of days, as you saw in the example on the previous slide as well. It takes usually a couple of cycles to start being like significantly accurate. Before that, I mean, it does have a prediction, but the prediction is so wide that you would once again be only hitting the very extremes. So basically, the unsupervised part means that we don't teach it manually. I mean, we don't show it examples. We don't show the machine learning job or the machine learning entity in the elastic stack. We don't like show any examples that this is an anomaly, this is fine, this is normal, and so on. But it's only getting the data and starting to look at it by its own capabilities and defining the normality for itself. And of course, from that definition of normal, it is also able to detect abnormal, which is what the anomaly detection basically is. Like I said, I mean, next steps for us, it might be supervised learning, but so far we haven't yet seen necessarily a need for supervised learning. I mean, being able to give the machine learning job examples of how the like how the abnormalities usually kind of pop into the network. But the classification is probably where we will go. And the classification, if it starts working in a networking use case perfectly, it very well might be that it changes the policy planes of networks very significantly. But today, I mean, very practical. These are maybe you can call them baby steps, but they're like the initial use cases that we're working with. We are measuring the using Telia SD-WAN, we measure the network performance, and we are kind of implementing machine learning for those results. We built a use case for kind of malicious host detection based on port scanning, but this was a little bit, I would probably call it like an academical exercise. It was a little bit theoretical, but we did kind of take into account in that use case, these variances, the cyclical nature, and the growth of the network over time. Application monitoring use cases, I mean, we are initially, or in the initial steps of being able to predict with machine learning TCP connection problems, DHCP DNS problems, path MTU problems. We are also looking at the use cases of being able to predict problems with mobile uplinks, looking at the specific like variables of RSSI, RSRP, RSRQ in the mobile network signal strength basically, and the change and variation in those over time, and being able to predict that, hey, this site is probably going to have a problem tomorrow or this afternoon. And one of the key use cases for us is the gateway throughput and health status monitoring. And we are now in a phase where we are doing this internally for us. I mean, it is input for our DevOps teams and humans, human operators on Telia side. But the next step is to kind of make it external, and we are collaborating with Nokia there. You can take the next slide, please. I mean, on the outputs, and I suppose I already covered this a little bit. I mean, the SD-WAN overall, it's a huge enabler for this. We have the programmability of the network. We have the APIs from which we can fetch the information, both in the Elastic platform, and we can fetch information from the SD-WAN platform itself, and we can enrich the alerts based on that, and that's what we do. I mean, we are at this point in time alarming notifying our operators that, hey, we have a problem here and there, and please take a look. But definitely the next step that we see is that we would go for some type of a closed loop automation. It would be simple. I mean, we wouldn't give all the keys to the whole network for the machine learning job and the automation there, but we would let it start by doing some kind of adjustments in the network, so that we know that adjustment is only a change in the configuration. It's not like a total revamp, and whatever that adjustment is, it won't like break the network. Then, I mean, what we are looking as well is to build totally new types of service models from machine learning as well. And this is especially like the area which I'm very interested of. But at this point in time, this is also like relatively simple. We see possibilities to upsell based on the information that we get from the machine learning. Like we can point to the customers that, hey, machine learning job is pointing out that there is a point of congestion, or there will be a point of congestion in the network in close future, and maybe we should deploy more capacity there. And it is usually relatively strong argument to do so. And as well, I mean, this is tied to the mobile network signal strength use case, the external antenna installations I mean, theoretically, why not for Wi-Fi as well, but we are not looking at that so actively at this point in time. So now it's the mobile network and external antenna installations. So of course, I mean, our SD-WAN devices, they come with those so to say, external antennas behind the device. But I mean, this means cabling and deploying maybe a outdoor antenna or something along those lines, 10 meters away from the SD-WAN CP that we have deployed at customer premises. And moving on forward, I mean, what we are really interested in is kind of making this more complex and from the complexity actually more productive as well. And the way to do that is to start combining multiple variables for the machine learning. I mean, we are still looking at the customer networks as a relatively like closed systems with no connectivity to outside or no correlation to anything outside. But it is really easy to identify possibilities of doing such correlation. I mean, in the capacity predictions, for example, for the machine learning in the SD-WAN, I mean, it would make a lot of sense to start correlating the capacities in the SD-WAN internet breakout, for instance, or SD-WAN sites to some kind of a node in the network elsewhere, totally outside of SD-WAN, probably in the core edge infrastructure of Telia. And if there is an increase in the core router throughput at a certain point in time, it is probably quite normal that such similar increase happens also in the SD-WAN network. And machine learning with Elastic definitely allows us to do this one as well, but we haven't yet proceeded so far. We could move to the next slide. And like I think I have mentioned, we are doing this based on Telia SD-WAN product that is based on Nokia Nuage. And it just so happens that also Nokia is using Elasticsearch cluster as a very integral part of the product there. And they're the two components of the Elasticsearch itself. That is the database product that offers you the capabilities of data search and storage. And it can be used as a time series database as well, even though that's not the only use case for it. And then additionally, especially the Kibana like visualization component, that is the component in the Elastic Stack that includes the machine learning capability. So that was like the, let's say, cue for us that hey, this is really like easily available for us. For the production type of deployments, of course, I mean, we are implementing additional Elastic clusters and so on, so that we don't stress the SD-WAN platform with these machine learning CPU and disk consumption problems. So it is happening kind of on the side, but still, I mean, this is a huge enabler for us because for instance, copying data from a Elastic cluster to another Elastic cluster is way easier than would be copying data from totally different database product to Elasticsearch. I mean, there would have to be pretty hefty conversion in place that wouldn't make it so real time anymore, and in itself already consumes quite a lot of resources. And as a product, of course, Telia SD-WAN and the Nokia Nuage, it has like these capabilities of collecting that big data type of a network telemetry information, and the list of items that we are collecting and storing into that Elastic database, it is huge. I mean, like I have mentioned, application information, deep packet inspection. I mean, we know of how much traffic is going for the underlay, how much traffic is going for the underlay. We know the access list statistics. We know the policy statistics. If we are building IKE tunnels and sending traffic to those, for instance, into Azure, AVS, whatnot, other firewalls, we see statistics from those. We know the CP devices themselves. I mean, their health status, like how much memory they're consuming, how much storage they have a small, SSDs inside of them, how much CPU they're using, temperatures, CPU temperatures, fan speeds, etc. I mean, we could start predicting even device failures with machine learning. I mean, that's a really interesting use case based on, I mean, CPU, fan speeds, temperatures, memory usage, and so on. I mean, increased memory usage could probably like predict that something is going wrong on the software level within that one single CP, or increased temperatures and fan speeds could indicate that the device is not placed that well, or that it's having some kind of hardware problem. Redundant PSUs, SASE intrusion as well.
1 minute, please.
Yeah. This is actually my last slide. So. And then for the traffic data, I mean, we of course know how much traffic is passing in the physical interfaces, how much traffic is passing for certain reports, for subnets and different QSQs. We know the statistics from the Wi-Fi. We are not yet using Wi-Fi data for the machine learning use cases, and then there is the network performance, which is one of the kind of a main use case that we are implementing machine learning at this point in time for. It's the kind of a quality analysis and prediction of the network because we are mostly focusing on the delay, jitter, and packet loss in the overlay network. But yeah, actually, this does cover my presentation.
Thank you very much. Thank you very much. You did get a compliment, by the way, online. That is an interesting presentation. I don't know if you saw the comment. Any questions? Okay, we have a question. Here, you can take the microphone from there. Okay.
Jean-Marc Cuzet, Octera Networks. Thank you very much. It was a really good presentation, and I don't think I've seen such a conference coming from a service provider so deep insights about why using machine learning, what it brings to the table, and all the things that you mentioned, the limit of static threshold, the focus on unsupervised learning and classification. All these things are giving really great direction to the audience. So thank you. I have a question. You mentioned some key use case at some point in the slides, 3 bullet points, TCP performance or connections, DHCP, DNS. You mentioned 3 use case, and I would just wanted to ask you if you could just elaborate a little bit more about what you are focusing on here.
Yeah, I mean, some of those, or I would maybe divide the use cases into 2 categories at this point in time. So we are looking at potential network congestion, so the throughput situation and the kind of evolution of the throughput, knowing that certain nodes in the network have certain limitations coming from licensing, coming from physical limitation of the devices, and so on. And being able to predict this congestion before it occurs is kind of a key thing for us. Secondly, we're looking at the network, like let's call it network quality, and that's like when the use cases where we are mostly looking at these quality characteristics like jitter, packet loss, and latency. And I mean, this is also about being able to predict if there is going to be some type of a lessening in the quality, like a brownout or other type of a situation in the network, and we can inform of the customer beforehand, and we can probably, if we know it beforehand early enough, we can implement even some alternative choices like additional uplinks or like change from mobile uplink to fixed uplink for certain applications and using application level routing and so on. But I mean, at this point in time, it's about predicting congestions in the network as well as being able to know of some quality problems in the network before they occur.
Okay, thank you very much. Any other question? If not, then we'll head out for the coffee break, and you can also take coffee if you want.
Thank you.
And we'll meet here again at 11. Thank you.
Thank you.